welcome to the Explainer. Right now, you're likely watching this on a screen powered by electricity. But have you ever stopped to think about where exactly that power comes from? Today, we're diving right into the heart of thermal power generation. We're going to unpack the hyper-efficient mechanical assembly line that literally transforms a solid, dusty rock into the energy powering your life.
So, how exactly does a rock power an entire city? Well, to figure that out, we're going to trace the crazy, rapid journey of a single piece of coal as it blasts through a modern power plant. We'll keep our breakdown as concise and direct as a mechanical blueprint. Let's get into it.
Step 1. Preparing the coal.
Now, you might be picturing an old steam locomotive where someone is just shoveling giant boulders of coal into a roaring fire, right? Well, actually, scratch that. Modern plants don't work like that at all. The fuel has to be meticulously prepped. Raw coal gets fed from bunkers directly into heavy-duty bull mills, where it is violently crushed by massive rotating rollers. And I mean crushed, until about 70 to 80% of it can literally pass right through a microscopic 200-mesh sieve. To put that into perspective, we're talking about particles ground down to between 5 and 400 micrometers. It's essentially pulverized dust, kind of like talcum powder. Once it's that fine, a huge blast of hot primary air catches this dust and blows it directly into the combustion chamber.
Moving on to step 2, combustion and steam.
Okay, so once inside this massive furnace, that powdered coal ignites right in mid-air suspension, and it gets incredibly hot. We're talking searing temperatures hitting anywhere from 1,300 up to 1,700 degrees Celsius. In a microscopic flash, almost too fast to comprehend, each individual particle goes through 4 distinct stages. First, it dries out instantly. Second, devolatilization happens, which is just a fancy way of saying it releases its trapped gases and tars. Third, those volatile gases ignite. And finally, the remaining solid char just burns completely away. So what is all this intense, suspended fire actually doing? Basically, it's just boiling water. Seriously, the inside of the furnace is lined with miles of tubes filled with circulating water. It acts just like a giant, high-pressure kettle, absorbing all that insane thermal energy to create steam. But how well this giant kettle works all comes down to thermodynamics. See, by pushing the water pressure up to an absolutely mind-blowing 4,640 psi and cranking temperatures over 1,100 degrees Fahrenheit, modern ultra-supercritical plants can keep water fluid way past its normal atmospheric boiling point. It's crazy engineering, but it extracts the absolute maximum efficiency, converting up to 46% of the coal's raw energy directly into electricity.
All right, step 3, turning steam into electricity.
Now we have to convert all that intense thermal energy into actual mechanical power. To do this, the highly pressurized steam is piped through control valves directly into a turbine. You can kind of think of it like a massive high-pressure pinwheel. The steam hits those turbine blades with just incredible force, rapidly spinning a central shaft that's hooked up to a massive magnetic generator. And as that generator spins, boom, it creates the electrical current that gets dispatched straight to the grid.
Which brings us to step 4, cleaning the flue gas.
So, the electricity is flowing, but the physical process isn't over yet. The exhaust coming off that furnace is full of smoke, heavy ash, and fly ash that absolutely must be thoroughly scrubbed before it reaches the chimney. This crucial cleanup step is handled by something called an electrostatic precipitator, or an ESP for short. This device sits right between the furnace and the exhaust stack, and its whole job is to prevent that fly ash from causing respiratory or environmental damage.
The way this works is actually super cool. It's essentially industrial-scale static electricity. You know, kind of like rubbing a balloon on your hair. Inside the ESP, electrodes create this strong negative electric field, which blasts a negative charge onto the incoming ash particles. Then, acting just like magnets, that negatively charged ash flies toward and sticks to these large, positively charged collector plates.
Once a good layer of dust accumulates on those positive plates, a mechanical wrapping system kicks in. And yes, wrapping means mechanical hammers literally rap against or vibrate the plates to shake all that accumulated dust free. Gravity then just drops the ash straight down into collection hoppers below. From there, it's safely conveyed away, and get this, it's often sold as a valuable industrial byproduct to cement manufacturers. Thanks to this incredibly clever, large-scale application of electrostatic force, modern ESPs boast a staggering dust removal efficiency of up to 99.9%. That is wild, right? It ensures the vast majority of particulates never actually reach the atmosphere.
Finally, let's look at step 5, the future of coal. As the global grid demands cleaner, more sustainable energy, this classic assembly line process is getting some radical updates. One of the biggest game changers is a technology called Integrated Gasification Combined Cycle, or IGCC. Instead of burning raw coal like we just talked about, these new plants literally transform the coal into a synthetic gas first. This is a real game changer because it allows operators to extract pollutants like sulfur and carbon dioxide before combustion ever even occurs.
But it's not just about mechanical hardware updates. Advanced digital analytics are now being overlaid onto these massive plants. Operators are using real-time software to totally optimize fuel dispatch, run predictive maintenance schedules, and vastly improve their ramp rates. Basically, that means they can increase or decrease their power output way faster. And that is absolutely crucial because it lets these plants better complement fluctuating renewable sources on the grid, like wind and solar. The impact of these software upgrades is massive. By fully embracing this digital transformation across the industry, global coal operations have the potential to reduce CO2 emissions by a staggering 469 million metric tons. It really is a prime example of optimizing a legacy process with cutting-edge modern data.
Which really leaves us with one big question. As technology pushes the very boundaries of thermodynamics, software analytics, and gasification, how much cleaner and more efficient can this 19th century invention actually become? How will this fundamental process continue to adapt to the ultra-demanding 21st century grid? It's a fascinating engineering challenge unfolding right in front of us. Thanks so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.